Gottfried Wilhelm von Leibniz was born July 1, 1646 in modern-day Leipzig, Germany. Unlike fellow creator of calculus Newton, Leibniz was not born a math prodigy, but rather came to understand mathematics as he became older. By no means was Leibniz just a mathematician. Indeed, his interests included metaphysics, a branch of philosophy which we will come back to later, law, economics, politics, logic, and obviously mathematics. It was in the mid-1670s that Leibniz made the breakthrough in calculus. He one day realized that the tangent to a curve was the ratio of extremely small increments of y to extremely small increments of x, and that the area underneath a curve was the sum of an infinite number of tiny rectangles, with the width being the extremely small x increments and the height being the y value. He thus was able to determine that tangents and area, or as we say today, derivatives and integrals, are inverses of each other. His notation for the derivative was dy over dx, with a d in front of each variable, showing the fact that it is a very small interval. And for integration, he used an elongated s, which is still in use today. What is most fascinating about Leibnizian calculus is not the actual laws themselves, as Newton discovered most all of these laws before Leibniz, unbeknownst to Leibniz himself, of course. What is most fascinating is the concept of the infinitesimal on which he based all of his calculus, and which actually had root in his background of metaphysics, or the philosophy of existence itself. The metaphysical theory with which Leibniz associated himself was one where the world is composed of infinitely many, infinitely small entities called monads. Leibniz's general belief that something could be infinitely small, yet not be zero, was controversial, but was the basis of all his calculus. Today, we have the term known as the limit, which is the first thing one learns in a calculus class because it is the basis of all calculus. We use limits to show that x approaches a value but never reaches it, thus avoiding the controversy of using a whole new class of numbers to describe calculus. Leibniz, however, was never afraid of a little controversy. The terms dy and dx were called by Leibniz differentials, and were infinitely small intervals that weren't zero but weren't a number greater than zero either, because they were their own class of numbers called infinitesimals. Four properties define these numbers. 1. Dx is indistinguishable from 0. 2. Dx is neither equal nor unequal to 0. 3. Dx squared equals 0. And 4. Dx becomes vanishingly small. Leibniz was steadfast in his belief in the legitimacy of his new numbers. Even when infinitesimals were all but banned from mathematics, still a few believers remained. And finally, in the 20th century, some 300 years after Leibniz's work, fellow German mathematician Abraham Robinson proved the legitimacy of Leibniz's infinitesimal numbers as used in calculus. Leibniz died in 1716, but is remembered as one of the greatest ever mathematicians, and his calculus concepts and notations are still widely used today at all levels of calculus.